Since we have completed TQ class as template, so let's test for another data type. Here we have tested for integer, so let's copy the code for integer test and then do it for some other class as well, some other type as well. So copy and paste that. Now it's for double type. So here we define another variable. Let's name it as QQ, and that's for double type data. So QQ instead of Q. Let's paste, change it as double Q. And then since we are giving integer type as data, let's change it to a double type data. So when you do push it, let's add 0.15 times. Instead of doing 0.5 directly, I just add 0.15 times to explaining to explain some other things you need to consider if you deal with a non-integer type like double. So at front we added a 0 plus 0.5, that's what you expect, but in back is dependent upon variable I, so I plus 0.5 is the value we anticipate. So in the next loop, the front is always I, but it's I plus 0.5 is what you expect. On the back, always the value is the I plus 0.5 is the value, then that's what you expect. So let's compile the program and then let's run it. So what it says is that at line 35, this assertion failed. So line 35 is this line. So this assertion failed, but it should be the equal value, but the program running says it's not equal. So let's do some debugging before we do assertion. Let's see what value we get. So QQ back, and then let's have one blank, and then let's print I plus 0.5. Let's see what you get. So compile again and run it. Those values are the same. So why do we have a problem? The first iteration when I is 0, that's okay, but the second iteration it failed. So second iteration when I is 1, this one and this ones are not the same. So what's happening is called truncation in representing real number or floating point numbers. Let me show you what's happening first. So since what we are displaying is to certain precision, after decimal point, the two certain digits are displayed by default, but we can change it. Set precision manipulator say that show me up to 20 digits after decimal point, so that we can see very detailed value. The set precision is in IO manip library, IO manip library. So let's just see what's happening there. If I run it now, we can see that in comparison, what you get is a 1.5 and the many zeros are 4441, and then this is 1.5 second one. So when you do comparison down here, this one, we read the back of the queue is 1.5, and then after several zeros, there is some small value appended. But that is compared with I plus 0.5, 1.5. So that equality failed because that. So what's happening? What we pushed is exactly I plus 0.5, but what we get is not exactly I plus 0.5. That's a truncation in real number representation or floating point in C++. That is in double or float type in C++ is represented by certain bits. It's 8 bytes, so 64-bit is used. But using 64-bit, we can represent only finite number of digits, a number of values. But in math, double or real number represent infinite values is represented. So in line number, as you imagine, real number, we have a 0, here is a positive infinity, and here is a negative infinity. But even between 0 and 1, we have a infinite number of values in math, but in a double type can represent only this many out of 64 bits. So in representation C++ language, in many other language, we do approximation. So we are unable to represent all possible real numbers in math, so we just pick and choose some of those ones. So close to 0 we represent many, but as we go bigger and bigger value, so 1 and then next one is like that. We have a discrete values are represented by programming language double type. So if some operations of a double, mathematically it may end up some value in between the two. So in double type, you can represent that this one and next one is there, but here's some unrepresented values. But if this two operation, this two value ends up somewhere in between two representable values in double type, then it's approximated. So because of that, we have some errors, a truncation error when you do operations of a non-integer type, double type. So that's why, because of that, some accumulated those small errors. The number represented in 1.5 out of this equation may have some small errors there. So when you write the program, and then if you want to compare two non-integer types like that, never ever use equal one. Equal is only for integers. For if it's not integer, do not compare equality with equal, but take the difference, and then if the difference is small enough, then say it as equal. So here, what you need to do is there is a fabs function from CMath library, which takes one value. So subtract the difference between the two values, and then fabs returns the absolute value of the difference. So if the difference is small enough, then if difference is small enough, then consider that's the same. So that's the idea. Then in this case, we need to define what is E. So define double E. So how small is small enough in this one? So depending on your application, the small enough is different. So if you use some money values, a double as a money value, a dollar and cents, then 0.01 is 1 cent, so less than 1 cent should be the same, and the like. So depending on application, you can define how small is small enough. In this comparison, we can define like that. We can give just several zeros and 1. If a difference is this small, then it's the same one. So then instead of a direct comparison, always find the difference and then see if the difference is small enough. So in this case, for safety, we could do same idea. So take the difference between the two, then find absolute of that, And then if it's small enough, then consider that's the same. So now we have done for that. And then also in comparison down here, we do the same thing. So here, FABS, compute the difference between two values. Then if difference is small enough, consider that's the equality. So here we do same thing, take the difference between the two. If it's small enough, then let's consider it as a equality. And then FABS, the absolute function, is defined in C math library. So we need to include the C math library. Now let's compile the program. And this message may come too many times, so let's take that out. Compile the program and then run it. Then all assertions successfully done. So here, when you compare non-integer type numbers, always take the difference, and then if the difference is small enough, then consider as equality. That's an important thing that programmers should remember.